Hi there. What we're talking about today are phase change diagrams. Let me show you a picture of a phase change diagram. This is a picture of a phase change diagram. You can see there's different regions of it. There's a solid, the ice region, because we're looking at H2O water here. The water, the liquid region's on top, and then the water vapor or the gases on the bottom part. The question I have for you is, what is the melting point of water? In other words, what temperature does water melt at? You might be thinking 32 degrees Fahrenheit. Remember in science class, you got to think about Celsius. Celsius would be 0 degrees Celsius. So the melting point of water is 0 degrees Celsius. What's the freezing point of water? Well, melting is when it goes from a solid to a liquid. That happens at 0 degrees. And freezing is when it goes from a liquid to a solid. That's the same state of matter change. The freezing point and melting point of water are both at 0 degrees Celsius. We can look it up on this chart to see exactly what temperature anything melts or freezes at. So normal would be 1 atmospheric pressure, that would be if we're at sea level, which, if you take a look at when something melts or freezes, that's when it goes from our solid state, which is this part, to the liquid state. And that happens at this point right here on the chart. If you follow that down, that's 0 degrees Celsius. But you can see on this chart what we can do is we can actually change the melting point or freezing point of water by just changing the pressure. Let's increase the pressure to something drastic like 218 atmospheres. I know that's pretty drastic. Here's our melting point then, which if we bring it down brings us to a negative temperature. So every change in the state of matter has to do with pressure as well as temperature. Most of the time we keep our pressure the same at 1 atmosphere, so we don't really have to talk about pressure very much. But we are looking at states of matter, so here we've got to start thinking about the different pressures and temperatures of things. Okay. If we're looking further into how something melts or freezes, we've got ice. Ice is actually a beautiful crystal. If you look at it through this way, it makes this honeycomb shape, which you can see on the picture there. Otherwise, it kind of looks all jiggy-jaggy, but if you look at it a certain way, it makes a beautiful honeycomb shape. Now, when water goes from solid to liquid, it's that the two waters separate their intermolecular forces. It's not that the bonds are breaking, as a recap here. That would be a chemical change, and melting and freezing is not a chemical change. It's that our solid ice is moving into the liquid state. They're slowly separating or having their intermolecular attractions broken so they can move anywhere next to each other. A solid is very rigidly staying in place and vibrating. A liquid can kind of slide past each other because its intermolecular attractions are made and broken and made and broken. And a solid is intermolecular attractions are staying. In a liquid, they're made and broken. Let's look a little further at what this phase change diagram kind of shows us. We've got the solid, liquid, gas part. We also have the melting and freezing. You can look, this chart's a little bit different because it's not for water. We can have something go from a liquid to a gas. That's this boundary, where you're going to vaporize or condense. Condensing is becoming gas to a liquid, or vaporize liquid to a gas. We can have our sublimation and deposition happening when a solid goes to a gas, or vice versa, gas goes to a solid. And we can look up any temperature and pressure that those are at. Other things to note about this is these points in the middle, right? Let's take a look at this interesting one in the very middle. It's called the triple point. The triple point. I want to show you a video of that. Triple point. Okay. So they did a lot of stuff as they were leading up to this, but what you start to see is they've got a set pressure and a set temperature inside this container. This is a triple point of an alcohol. You can see that crystal that's forming, that's the solid. And now you can see bubbles, that's the gas. So I can still see the solid crystals, the bubbles gas, and yet everything's moving because it's a liquid. This is a triple point for this alcohol. There's a solid, a liquid, and a gas happening all at the same time. And you can see all the characteristics of them. Bubbles are still happening, the solid crystals are still there, and the liquid part, everything is still kind of moving. Okay, back to our diagram. So you can see that the triple point is the point at which a solid, liquid, and gas is all happening in the same container. It's a set temperature and pressure. And there's a triple point for every substance, because we can have a phase change diagram for every substance. Another one to look at is this supercritical fluid. This right here, notice the line of the liquid and gas has gone up, but now it's at a set point. It's called the critical point. That's at the point where we can't tell, is it a liquid? Is it a gas? I can't really tell what it is. This professor is going to tell us about it.
This is a demonstration that we use for school children and others about explaining the sort of research I do. So there is a little cell here, and this is a television camera which goes on a big picture up here. Now, the important thing is that this is not a video. So if you look, if I shake the table, the whole thing shakes. And what is actually in here in the picture, there is a liquid sealed into a cell with gas above it. The vapour, like it could be water and steam. It's not water, but it's similar. So if we start heating this,
what did you do just then?
I just flicked this switch and switched on the heater, so the temperature you can see is going up. And as the temperature goes up, this begins to boil. So you can see it begins to boil, and as it boils, material goes from the liquid into the gas. And as it goes into the gas gets denser because it can't escape. It's a sealed cell, but the liquid, because it's being heated, expands. So this becomes less dense, that becomes denser, and eventually they become the same density, and the line in between it completely disappears. So you can see it's almost gone now, and what happens is that you then have a gas which has about half the density of the liquid, and this is a so-called supercritical fluid. And I first saw this demonstration, or one similar to this, about 20 years ago, and I was completely hooked. And I've been researching on this ever since. Now it's even more fun if you cool it down. So if I flip the switch, it starts it cooling, and the temperature starts dropping. It takes a bit of time because we've just been heating it. But, so you can see the temperature's beginning to go down. It's going down quite well. And as you go up here, if you look, imagine that we have a gas. It's a bit cloudy because there's some glue dissolved in here, but ignore the cloudiness. And what we've got here is a gas, and as we cool it down, it will suddenly separate again into liquid and a gas. And the bubbles of the gas will go upwards, and the droplets of liquid, because they're denser, will go down. So you can see it's just about to go now. It goes at 45 degrees. And you get a sort of storm. And I demonstrate this sometimes several times a day if I have lots of visitors, and I still get hooked on this. Now, if you're very observant, you'll see there now appears to be less liquid than there was before, because there's still droplets of liquids coming down here. And so I keep this in my office really for two reasons.
Okay. I love how nerdy he is about it. That's my favorite part. We should all be nerdy about something, and that's his. Okay, so we saw the supercritical fluid. Since the liquid and gas have the same density-ish in that supercritical fluid, we can't tell one from the other. And so we can't have a line to show the different phase changes. That happens at our critical point. The pressure and temperature at which that happens is called the critical point. Okay, going back to our melting of solid. So we've got this beautiful crystal structure you can see, and then as a liquid water it kind of folds in. This is an important part because if you look at density, so look at the picture as a solid. As a solid, ice has less density. It is lower in density because there's less mass per unit volume because all the molecules are kind of spaced out. They take up a lot of space with the same mass. As a liquid, water has more dense because all the particles are closer to each other. That's why ice floats on top of water. And that's also why we get this curve here. So if you notice this curve, this slant is kind of slanted backwards. That's an important part actually, and something that's really unique for water. Water and mercury have this backward slant, while most substances, if you take a look at the line now, have a forward slant or even forward curve, because most, if not all, almost, substances have a solid which is more dense than a liquid which is less dense. But water and mercury are kind of these differences, and that's why it's got the backward slant. So most times our phase diagrams will have this forward slant, like carbon dioxide has. Okay, you're headed to the lab. If you have any questions, please feel free to ask me, and I'll do the best I can to help you. Good luck.